Hello, welcome to Business Statistics. In this lecture, I will discuss about comparison of two population proportions. Suppose we have two populations. This is population 1 and this is population 2. And we are interested in comparing their proportions. So the proportion of population 1 is given by pi 1 and the proportion of population 2 is given by pi 2. So we are interested in knowing whether pi 1 is different from pi 2. So that is pi 1 not equal to pi 2, or pi 1 greater than pi 2, or pi 1 less than pi 2. So you might know the definition of proportions, which is for pi 1 it would be x1, capital X1 divided by n1. So that's the number of observation having certain characteristics is our x1, and n1 is the total number of observations in population 1. Similarly, for population 2 we can write it as capital X2 divided by n2, where x2 is the number of observations having certain characteristics and n2 is the total number of observations in population 2. So that's the definition of proportion. Now if you see this pi 1 not equal to pi 2, in hypothesis testing it is a two-tailed test, and pi 1 greater than pi 2 and pi 1 less than pi 2, these two are one-tailed test. So now we wanted to compare the proportions of the two populations. It's challenging because population firstly have a lot of data points and secondly they are continuously changing. So we can take a sample. So I will take a sample. So this is from population 1, so this is sample 1. And this would be sample 2. So the facts about sample 1 is mostly in terms of proportion. It can be represented by P1 hat, and I will take a sample of size n1. So here the proportion is represented by small x1 divided by n1. Again, small x1 is the number of observations having certain characteristics, and n1 is the sample size. Similarly, here we will have P2 hat and n2. So P2 is represented by small x2 divided by n2. So x2 is again number of observations having certain characteristics, and n2 is the sample size of the size of the sample 2. So once we have this, we can kind of try to write these as we wrote in our previous lectures as a difference. So I can say this is pi 1 minus pi 2 not equal to 0. This one, the second one, I can say pi 1 minus pi 2 greater than 0. And the third one, I can say pi 1 minus pi 2 less than 0. So we converted all of them into differences. Now if you see this population, this sample proportion here serves as an estimate for population proportion, and then proportion of a sample 2 serves as an estimate for pi 2. So that means I can substitute, instead of pi 1 I can say p1 hat, and instead of pi 2 I can say p2 hat. So this p1 minus p2 serves as an estimator for pi 1 minus pi 2. And now if the sample size is large, we can use z statistics. So we wanted n1 to be very large. So one of the tests which we do in proportions is n1 multiplied by p1 hat if it is greater than 5, it's a large sample. So it's a large sample, so we can invoke central limit theorem and say that sample looks normal. So sample is normal if it fulfills this criteria n1 p1 hat, because the sample size is large. Similarly here we can do the same thing and say if n1 n2 p2 hat is greater than or equal to 5, then this sample would also be normal. So they follow normal distribution. So since both the distributions are normal, P1 hat minus P2 hat distribution would also be normal. So if we establish that as normal based on central limit theorem, we need standard deviation, which can be represented by sigma P1 hat minus P2 hat. So that's the standard deviation of the difference of the mean, and it is represented by the formula P1 hat square root of P1 hat minus 1 minus P1 hat divided by N1 plus P2 hat 1 minus P2 hat divided by N2. So this is the standard deviation or standard error of the difference of the proportions. So this can also be written as, so the standard deviation of the proportion of the difference of the proportions can also be written as, we can use any one of these formulas, P bar 1 minus P bar 1 by N1 plus 1 by N2. So where P bar is given by x1, small x1, so this would be the sample x1 plus x2 divided by n1 plus n2. So these x1 and x2 and n1 and n2 refers to samples. So this P bar is called weighted average of the proportions. So that is the concept. So we converted the proportions. If the sample size is large enough, we can invoke central limit theorem and say that the difference in the proportions will also behave normal, and then we can use the P1 hat minus P2 hat and the standard deviation of the difference in the normal distribution. So now that we have done this, we will discuss about hypothesis testing and confidence interval for proportions. So this is hypothesis testing. So the first step of hypothesis testing is to define your hypothesis. So we define our hypothesis. So our H null The statistical definition of our hypothesis testing for proportions is given by pi 1 minus pi 2 equal to 0, and then the alternative for this would be pi 1 minus pi 2 not equal to 0. So this is a two-tailed test because we can test on both sides. Again, the second case would be H null, pi 1 minus pi 2 greater than or equal to 0. Our alternative would be pi 1 minus pi 2 less than 0, and then our null hypothesis in the third case is pi 1 minus pi 2 less than or equal to 0, and the alternative would be pi 1 minus pi 2 greater than 0. So these two are one-tailed tests because we can test them only on one side of the normal distribution curve. So the next step would be to compare the test statistic with critical value. So compare test statistic with critical value. So to do the test statistic, here we will use a z-stat. So we will be looking at the criteria n1 p1 hat is greater than or equal to 5 and n2 p2 hat is greater than or equal to 5. Then we can use z statistics. So the formula for z stat would be p1 hat minus p2 hat minus pi 1 minus pi 2 divided by square root of p1 hat 1 minus p1 hat divided by n1 plus p2 hat 1 minus p2 hat divided by n2. So this is p2 hat. So there is another formula which we can use, which is again p1 hat minus p2 hat minus pi 1 minus pi 2 divided by square root of p bar 1 minus p bar one by n1 plus 1 by n2. So where p bar is equal to small x1 plus small x2 divided by n1 plus n2. So that's the formula which we will be using. So again we know this is an estimator. This whole thing is the standard error or the standard deviation of the difference of the proportion. This is hypothesized difference. And this is the weighted average. So the next step would be to get a critical value from our z table. So we have two critical values. One is z alpha over 2 if it is a two-tailed test, and z alpha if it is a one-tailed test. And then finally we make conclusions. So now that we studied about hypothesis testing, let's discuss the confidence interval. So 1 minus alpha multiplied by 100 confidence interval. Again, alpha is a significance level, so alpha is significance level. So the formula for 1 minus alpha multiplied by 100 confidence interval is given by p1 hat minus p2 hat plus or minus z alpha over 2. So if we have a one tail, we will have only one bound, so this becomes z alpha, and then this is a two tail confidence interval, and then the formula is square root of p1 hat 1 minus p1 hat divided by n1 plus p2 hat one minus p2 hat divided by n2. So this is actually z alpha if it is one tail. So this whole expression is the margin of error. This is the margin of error, and this is the estimator. So that's the main concept of hypothesis testing. So let's solve a problem on this. Uh, so I have two statistics sections, section 1 and section 2, and I am claiming section 1 students have more students who like color red. So more students who like color red. So now I will define the population parameter or population proportion. So this is given by pi1, and then this is given by pi2. So the first step of the hypothesis testing is to define the hypothesis. So I will define my hypothesis, which is H null. So this is an alternative we have. So I am claiming more students like color red in my section 1. So that means pi1 should be greater than pi2. That would be my alternative. So my null hypothesis would be pi1 should be less than or equal to pi2. So what it means is I can convert this into difference. Pi1 minus pi2 less than or equal to 0, and this alternative would be pi1 minus pi2 greater than 0. So once we get our once we define our hypothesis, the next step of the hypothesis testing is to compare test statistic with critical value. So to get to do a test statistic, we need the sample statistics. So we take section 1 and take a sample from the section. So once we take a sample from the section, so this will be given. So in your problems, when you solve the problems, this will be given. So x1 is 20. So this is 20 students like color red, and n1 is 40. So again we will take another sample from section 2. So x1, this is small x1, so I will just so this is 25 students like color red, and our this is x2, this is n2. So we take a sample of 60 students. So now that we have the number of students who like color red and the sample size, we can determine the proportions. So the proportion for the sample 1, that is p1 hat, is given by x1 over n1. So that would be 20 over 40, that is 0.5. So for the proportion for sample 2, p2 hat, is given by x2 over n2. So that is 25 over 60, that is given by 0.4167. So to apply z stat, as we discussed, to apply z, we need to check whether the sample is large enough. So to check the first one, I will do n1 multiplied by p1 hat. So that is n1 is 40. So p1 hat, I will use a fraction value to make my calculations easy, 20 over 40. So that is 20, which is clearly greater than 5. So it's a large sample. So we can apply normal distribution because of central limit theorem. So n2 multiplied by p2 hat is equal to, again n2 is 60, and p2 hat, I will use the fraction value to make calculations easy, 25 divided by 60. So this is also going to give us 25, which is greater than 5. So the sample is large enough. Because of central limit theorem, our difference in proportions will behave normal. So we can use z is equal to our formula, z is equal to p1 hat minus p2 hat minus pi 1 minus pi 2 divided by So I will use the first formula which we wrote, p1 hat 1 minus p1 hat divided by n1 plus p2 hat 1 minus p2 hat divided by n2. So we will put the values. So that is p1 hat is 0.5, minus p2 hat is 0.4167, and this is pi 1 minus pi 2 is the hypothesized difference, so the hypothesized difference is 0 divided by square root of p1 hat is 0.5, 1 minus 0.5, n1 is 40, so that's 40, plus p2 hat is 0.4167 minus that is not minus, this is 1 minus, so I will do 1 minus, okay, I will erase this. So that is 1 minus 0.4167 divided by n2 is 60. So this whole expression, so I won't have a parenthesis here, I'll just remove that, erase that parenthesis. So this is going to give us, if we calculate this, it's going to give us a value of 0.820739. So that is our test statistic value. So the next thing is we need to calculate critical value. So we need to see whether it's a one-tailed test or a two-tailed test. So because we have a less than or equal to, it should be a one-tailed test. So we will have z alpha. So we will draw a curve, a normal distribution curve representing pi 1 minus pi 2. So this is a normal distribution curve. So the pi 1 minus pi 2 value would be 0 here. So this is a null hypothesis, pi 1 minus pi 2 curve. So we are looking for a critical value. If you see our null hypothesis, pi 1 minus pi 2 less than 0, so that less than or equal to 0, so that means we will have a upper bound or a upper limit. So this is z alpha. So this area would be alpha. So if you see pi 1 minus pi 2 less than or equal to 0, that means anything to the left of this curve is do not reject H null, and then anything to the right of this curve is reject H null. So once we have this, so we are looking our critical value alpha. So we want to get alpha, we need a confidence interval. So our confidence interval is suppose it's given as 95%. So that means 1 minus alpha is 0.95. So our alpha is 0.05. So we are looking, we wanted a z value that is z at 0.05. So as you know that our z curve from our z table, we always gives you the left side of the curve. So if this is negative z alpha, this can be positive z alpha. So we would look for negative z alpha and then we will convert it into positive from our table. So let's go to z table and look for 0.05, the z value. So here is our z table. So we are looking for a value 0.05. So our 0.05 would lie somewhere here. So I will highlight it. So we can take either 1 point. So that is negative 1.6, 4, or negative, so that's negative 1.64 or negative 1.65. so we can take any one of them. Let me take negative 1.64. So our z value here is negative 1.64. so once we convert that, it will become positive 1.64. so that means this value is 1.64. so now we will look at 0.82073. where does it lie? So if this point here is 1.64, 0.82 would lie to the left. So that's where it lies. So that is 0.820739. so it lies in do not reject region of H null. So our null hypothesis is true. So this is true. That means do not reject H null. That means my claim more students in section 1 is a wrong claim. So it's this claim is I don't have sufficient evidence to claim more students like color red. So that is hypothesis testing. So this is not true. I don't have any evidence. So once we have this, let's try to calculate the confidence interval. This is a one-tail test, and see how we can calculate a confidence interval. So this is 1 minus alpha confidence interval for the same problem. So our confidence interval, which we said was we wanted 95% confidence interval. So the formula for that which we discussed was P1 hat minus P2 hat plus or minus Z alpha over 2 square root of P1 hat 1 minus P1 hat plus divided by N1 P2 hat 1 minus P2 hat divided by N2. So this is the formula for confidence interval. Now this is for a two-tail because we had Z alpha. So for one tail it will be Z alpha. So now let's write our hypothesis first. H null was pi 1 minus pi 2 should be less than or equal to 0. That was what our section 1 and section 2 problems hypothesis was, and our alternative would be pi 1 minus pi 2 greater than 0. So obviously when we draw our normal distribution curve for our null hypothesis, or pi 1 minus pi 2, so this is pi 1 minus pi 2 curve. So this is 0, and we discussed anything, this is Z alpha, anything to the left is do not reject. So let me use a different color. So this is don't reject, H null, and this is reject, H null. So minus infinity to Z alpha, whatever it is, so this is the upper bound. So any one-tail test, if you see the limit, because we have only upper bound, no lower bound, so our interval would be minus infinity to P1 hat minus P2 hat. So now we have an upper bound, that means we only take a positive sign. If we had only the lower bound, we would have taken only negative sign. So we take plus Z alpha, because it's an one-tail test, square root of P1 hat 1 minus P1 hat divided by N1 plus P2 hat 1 minus p2 hat divided by n2. So we can put our values. We had our values previously. So our P1 which we got from hypothesis testing was 0.5 minus 0.4167 plus our Z alpha value which we got was 1.64 multiplied by square root of, so P1 hat would be 0.5 1 minus 0.5 divided by n1 is n1 would be 40 plus, so again this goes, square root goes to so the second one would be 0.4167, that was our P2 hat. 1 minus P2 hat is 0.4167 divided by n2 is 60. So that will be our limit. So if you calculate this, you will get negative infinity to the first part. This one would be 0.0833, and this second part, which is the margin of error, would be 0.16645. So this limit would be negative infinity to 0.24975. So now if you see your null hypothesis, pi1 minus pi2 less than or equal to 0, so that means we have negative infinity and it covers 0, so that means this should be true. That's why we don't reject, do not reject H null. Suppose if we I'm supposing it. Suppose if we would have got the limit like negative maybe, let's see, maybe we can use a different example. Negative infinity to negative 0.25. Again, pi1 minus pi2 would have been would cover, because we are saying pi1 minus pi2 less than or equal to 0. We have less values here, so again do not reject H null. So this is how you solve a confidence interval. So this concludes our lecture on comparing two population proportions. Thank you.